Hello and welcome to 10.3 on parametric equations and calculus. So we'll start with the idea of slope and tangent lines and then get into the second derivative to play around with concavity a little bit. So slope and tangent line, if x is some function of t and y is also some function of t, then dy dx we would find by g prime of t over f prime of t, which we can also express as dy dt over dx dt. Here we're of course going to assume dx dt is non-zero. So this is how we would find the slope of the curve at some point xy. Now if we want our second derivative, we basically do that same thing again. We take the derivative with respect to t of dy dx and divide it by dx dt. So for example, we can start with the parametric equation x is 6 cosine t and y is 8 sine t. And for this problem, t will be on the open interval 0 to 2 pi. So if I'm looking for the slope, I'll find dx dt. So that would be negative 6 sine t. I'll also need dy dt, which would be 8 cosine t. So our slope would be dy dx, so that's dy dt, 8 cosine t, divided by dx dt, negative 6 sine t, which is negative 4/3 cotangent t. So if they ask us about a horizontal tangent line, that is basically places where the numerator here is 0. So we just set 8 cosine t equal to 0, so cosine t equals 0, and on the open interval 0 to 2 pi that we're working in, that would happen at pi over 2 and 3 pi over 2. If we're looking for a vertical tangent line, that happens when we're dividing by 0, so we set the negative 6 sine t to 0. So sine t equals 0, and on our interval, that would happen at pi, since remember we threw out 0 and 2 pi. So they could ask us about a horizontal tangent line, a vertical tangent line, or they could ask us for the equation of a tangent line at a given point. So we'll look at the equation of the tangent line at 3 root 2, 4 root 2. So that's an x and a y. So x is 3 root 2. Remember from the other page, x is 6 cosine t. So 3 root 2 is 6 cosine t. divide both sides by 6, and root 2 over 2 is cosine of t. So then t would be the arc cosine of root 2 over 2. So that is either at pi over 4, so 45 degrees, or remember it is also a positive let's see, that would be basically negative pi over 4. So that's 3 pi over 2 plus pi over 4. So 6 pi over 4 plus 1 pi over 4, or 7 pi over 4. Now, to see if we get to keep one of them or both of them, we look at the other one. So our y-coordinate, remember from the other page, y was 8 sine of t. So 4 root 2 is 8 sine of t. So root 2 over 2 again is sine of t. Now sine of t is positive root 2 over 2 at either pi over 4 or 3 pi over 4. So just picture your unit circle here or here, the signs are positive. Here or here, the cosines are positive. But the only one that ran over both of them was the pi over 4. So here t is pi over 4. So we know the t value, so then to find the slope of the tangent line, we find dy dx. We remember from the previous page that that was negative 4 cosine t over 3 sine t, or negative 4/3 cotangent of t. So negative 4 cosine of pi over 4 is root 2 over 2. Sine of pi over 4, again, root 2 over 2. So we're right back at our negative 4/3. So that is our slope. So then we just use change in y, slope times change in x. So y minus 4 root 2 is our slope times our change in x. So y is negative 4/3 of x. Let's see, so that'd be plus 4 root 2 plus 4 root 2. So the 3's dropped, negative by a negative kicked us over to a positive. We kept the 4 and the root 2, and we moved the 4 root 2 to the other side. So y is negative 4/3 of x plus 8 root 2. That would be our tangent line at the given point. Now, if they ask for concavity at that point, then we're going for a second derivative. So recall dx dt was, let's see, dx dt was negative 6 sine t. And dy dx was negative 4 cosine t over 3 sine t. Or negative 4/3 cotangent t. So in this one, recall the derivative with respect to u of cotangent u is minus cosecant squared u times u prime. So our second derivative, differentiate this guy with respect to t. And divide by dx dt. So hang on to our -4/3 times negative cosecant squared t. T prime is just 1. And downstairs we saw dx dt, -6 sine of t. So first off we have a, let's see, 3 negatives, so negative coefficient, and 4/18 would be then 2/9, and we have cosecant squared t over sine t, but remember sine t at the bottom is the same as cosecant of t, so this is -2/9 cosecant cubed t, so this sine t moves upstairs. We can call it cosecant cubed t. So if we're looking for concavity, we figured out still t was, recall, pi/4. So -2/9 of 1 / sine cubed of pi/4. So that's -2/9 times 1/√2/2 cubed. If we're looking for concavity though, really all we're interested in is the sign. I have a negative times a positive. So this is negative, so this is concave down. Alright, so the other topic we get to play with in this section is the idea of arc length, building on a little mini review on section 7.4. So from 7.4, arc length S, integral from a to b, square root of 1 plus f prime of x quantity squared times dx. And for this one, we're going to temporarily flip out the f of x, just because we have that defined differently elsewhere in the problem. So we could alternately have written it as arc length integral from a to b, square root of 1 plus h prime of x quantity squared times dx. So in this section though, finding that derivative was a little bit different when we're working with parametric equations, but we're still looking from a to b. And to find a derivative, we have dy over dt divided by dx over dt. And we'll square that result. So all of this is under this big, messy, ugly looking square root, but it's not as bad as it might seem. we can, of course, get a common denominator going. So the 1 I can think of as 1 over 1, and each one then will have a dx dt squared on it. So integral from a to b, square root of dx dt squared over dx dt squared plus dy dt squared over dx dt squared times dx. Okay, so common denominator and square root of a square, we get just that piece out of it. So up top we have dx dt squared plus dy dt squared. Downstairs, square root of dx dt squared is dx dt times dx. Divide by a fraction, multiply by the reciprocal. So now I have dx dt squared plus dy dt squared times dt over dx times dx. And you guessed it, goodbye to our dx's. So our arc length in this section for parametric equations is square root of dx dt squared plus dy dt squared dt. Now I know the proofs are a little bit longer, a little bit challenging. If you're going any further at all in math, really try to read through the proofs in this book. Try to spend some time with them, get to know sort of the techniques and arguments that the authors use. You're going to see a ton more proofs if you move on in math, and those honestly are one of the more challenging parts of it. But if you get the hang of them early, it'll make the rest of your math career easier. All right, so my proofs PSA aside, let's look at an example here. So we'll find the arc length. Or x is, how would I pick, 3 plus 8 minus t to the 3/2, and y is 8t to the 3/2, and t is on the closed interval 0, 4. So we'll get our ingredients going first. Dx dt, derivative of a constant is always a 0. So we have 3/2 8 minus t to the 1/2 times -1. And a little cleanup. -3/2 8 minus t to the 1/2. Similarly, dy dt, 8 times 3/2, 4 by 3, 12, t to the 1/2. And we can write it with or without the radicals. If you'd like it with the radicals, if that helps you, go ahead and throw those in. Okay, so our arc length, integral from t is on the closed interval 0, 4. So integral from 0 to 4 of square root of -3/2 squared, square root of 8 minus t squared, plus 12 squared root t squared times dt. So our arc length, integral from 0 to 4, square root of, so we have 9/4 by 8 minus t plus 144t times dt. So we can do a little bit of distributing there. And let's see, so integral from 0 to 4. So 9/4 of 8, so 9 by 2, 18. Minus 9/4 of t plus 144t times dt. So our arc length, integral from 0 to 4. So we have a couple like terms there. So square root of 18 plus 567 over 4t. So that's multiply this guy top and bottom by 4 to get a common denominator going. Times dt. So then our arc length you can think of this as a 1/2 power if you want. 567 over 4t plus 18 1/2 times dt. These are t's here. So we have 567 over 4 t plus 18 to the 3/2, which means we'll need a 2/3 here. And we would also have multiplied by the derivative of the inside, which would be 567 over 4. So we'll also need the reciprocal 4 over 567. And we'll evaluate from 0 to 4. So then S is, so working with this outside part, 8 over 1701. And then just plugging in the 4 and the 0. So we have 585 to the 3/2 minus 18 to the 3/2. So S is 8, 1701. 585 root 585. So that's just taking care of the 3/2 power minus 18 root 18. And the root 18 if you want to turn that into 3 root 2 and turn that into 54 root 2. So arc length 8 over 1701. 585 root 585 minus 54 root 2. So a messy arc length, but an arc length, nevertheless. Okay, so our problems for 10.3. I would recommend 1 through 17 odd, 27 to 43 odd, and 49 to 53 odd. Okay, if you have any questions, please get in touch with me. Otherwise, I will see you next time for 10.4.